All right, section 5.3, we're going to solve trigonometric equations. So we're actually going to look and find the value of the variable in your equations. We split this up into 2 days. So these first two objectives are the day one. We end up doing them in the same class period, but what happens is we're going to split this up into 2 different sections of notes. So in the first part of these, we're going to just use basic algebra techniques to solve trig equations. And then we're also going to look at trig equations that look like quadratics. And then the second part, we're going to look at trig equations that have multiple angles and some where we have to use inverse trig functions to solve. So in order to solve a trig equation, you're going to use your basic algebra formulas. It's almost like your trig function is a variable. And you're going to essentially try to isolate that trig function so that way you can use your knowledge of your unit circle and solve for those variable values. So if we look at this first example, if we have 2 sine of x minus 1 equals 0, let's try to isolate the signs. So what we could do is we could say 2 sine of x equals 1, or the sine of x equals 1/2. So you have to think about your unit circle. We'll need to have this memorized still. And so your sine equals 1/2 when x is at pi over 6 and when x is at 5 pi over 6. Right? And that, again, that comes from your unit circle, kind of these values right here, is when your sine would be 1/2. And that's true if you go around your circle one time, those are the values. But if you went around another time, you would hit those values again. So if our domain is not restricted, we actually have to say x is pi over 6, and then we'll say plus 2 pi n, which means if you keep going around that circle, which is 2 pi, an infinite number of times, because this means for all integers n. So you go in a positive or a negative direction infinite times, you'll continue to hit that point. So same thing here, plus 2 pi n. Now, if this was restricted, if they said that you were on a domain from 0 to 2 pi, then that means that you're only going around once, and so you would only give those initial values. So this part right here means that there is no restriction on your domain, and this is that you could go around the circle as many times as you wanted to. Looking at this solution graphically, it's the idea that if you were to graph this function, it would hit 1/2 here, and then it would hit it again here and here, and those are all those values that it would equal 1/2, and then also this is that 5 pi over 6 mark right there. If we look at this next example, if you notice you have cosines on both sides, so sometimes it might help to try to get all of your functions to one side. So if we add cosine of x to both sides, we get 2 cosine x minus root 3 equals 0. And so now let's try to isolate that function. So we get 2 cosine x equals root 3, or cosine of x equals root 3 over 2. So again, this is unit circle. The cosine equals root 3 over 2 when x is pi over 6. If we look back, we're not restricted only to one rotation, so we would have to say plus 2 pi n, meaning it could keep going around. Or when x is 11 pi over 6 plus 2 pi n. So looking at this next one, we have a cosine squared. We don't have a cosine, so it doesn't look like a true quadratic equation where you have your ax squared plus bx plus c. So if we, again, could just isolate that trig function, we could say that we have 2 cosine squared equals 1, or cosine squared equals 1/2. And now if you have a squared on both sides, we could take the square root of both sides. So we would get that the cosine of x equals plus or minus And if I take the square root of 1, I get 1 over the square root of 2. And this doesn't look too familiar probably, but if we were to rationalize this denominator, so if we were to multiply by the square root of 2 over the square root of 2, we would get that the cosine of x equals plus or minus root 2 over 2. Right? And again, in your unit circle, the cosine is positive root 2 at pi over 4 and at 7 pi over 4. And it's negative root 2 over 2 at 3 pi over 4 and 5 pi over 4. So it's all of these values, but if you think about it, from here to here is 90 degrees, which is pi over 2. And from here to here is 90 degrees, which is pi over 2. So these are all equally spaced apart. The previous ones weren't, but these are all equally spaced apart. So we can actually say that x equals pi over 4, right? That's that first spot right here. And to get to the next one, we would just have to add pi over 2n. And every time you add pi over 2, right, if we start here, if we add pi over 2, we get here. And if we add another pi over 2, we get here and here and here. And it would just keep going around. And so that would hit all of those spots where our cosine would either equal positive root 2 over 2 or negative root 2 over 2. If we look at this next one, again, we have trig functions on both sides. Something that you need to consider is you don't want to ever divide by a trig function and get rid of it because you might be eliminating a solution if you do that. So if you can divide by a trig function and eliminate it, so if it looks like if you can divide by a trig function to eliminate one, then what you need to do instead is you need to move everything to one side and factor. Right, so if you feel like you want to divide and cancel, don't. Just get it all to one side. So let's go 2 cosine squared x minus 3 cosine x. Just set it equal to 0. So let's move it all to one side and then factor your GCF out. Factor whatever you were going to eliminate. So in this case, we could factor out a cosine. And if we factor out a cosine, we're left with 2 cosine x minus 3 equals 0. Right? And so now this is factored. We have, if you have 2 factors and they're equal to 0, what we can do is we can just set each factor equal to each other. So we would get cosine of x equals 0, or 2 cosine of x minus 3 equals 0. We're not restricted, so we're going to have to consider all the way around the circle. So the cosine equals 0, so your x coordinates equal 0 on the y-axis. And again, here, they're equally spaced apart. So if we went around this way, it would be pi that, then back up here would be another pi. So we could say it equals 0 when x is at pi over 2 plus pi n. Right? And again, if we think about what that means, is we know cosine equals 0 here at pi over 2. If I were to go around pi more, I would get to another solution. If I went around pi more again, I would get to another solution, and you would keep hitting those solutions. Over for this other factor, we would get 2 cosine x equals 3, or cosine x equals 3 halves. Now we know on the unit circle, cosine only goes up to 1. So if our cosine or our sine values are greater than 1, so here, because cosine of x is greater than 1, there's no solution for that part. Right? That's not going to contribute to any solutions. So our only solution that we have that would simplify would be at pi over 2 plus pi n. And then this last type that we're looking at today are the quadratics. And so when we have the quadratics, we've worked on this a little bit already with simplifying or showing two sides are the same, where we factored quadratics. And sometimes when we had those same terms, like if we had a sine squared and a sine, remember we would substitute in if that made it easier to factor. But you can only do that if you have the same function. If the functions are different, then you're probably going to have to use a trig identity to get those functions to be the same. All right, so here in this example, we need to find all solutions to 2 sine squared minus sine minus 1 equals 0. And here we're restricted on the interval for one rotation. So we're not going to add a plus 2 pi or plus 2 pi n to this. So what we're trying to solve, if we wanted to do a quick little substitution to make this just look a little bit more algebraic, we could say 2a squared minus a minus 1 equals 0. Right? And so if we factor this, this will factor, 2a squared will have factors of 2a and a, and negative 1 will have a factor of a plus 1 and a minus 1. So this will be your plus 1, and this will be your minus 1. So that way when you FOIL it back out, your middle term is negative a. Okay. So if we were to set these factors equal to 0, we could say 2a plus 1 equals 0, and a minus 1 equals 0. If we solve for a, we would a is negative 1/2, or a equals 1. But remember, we substituted a in for the sine of x. So at the end, we need to make sure we go back to that. So the sine of x equals negative 1/2, or the sine of x equals 1. So on your unit circle, when does the sine equal negative 1/2? Right, so we would say when x is 7 pi over 6 or 11 pi over 6. And then the sine equals 1 when your y-coordinate's 1. So that would be when x is at pi over 2. And those would be your only three solutions. Again, we're not going to put the plus 2 pi n because we were restricted just to one rotation around the circle to start.